Hello, my name is Zamaria Winston, and my final project focuses on accessible VR AR for science lab education. Overall, my final project challenges the issue dealing with underfunded schools lacking resources to conduct science labs, which overall disadvantages students in those underprivileged communities. Looking into the current tools that could potentially solve this issue, AR/VR is a modern solution. However, many existing VR and AR tools are high-end and not designed for accessibility, which ends up further excluding those communities that need it the most. The solution that I interpreted was developing an accessible 3D virtual lab in A-frame, which allows usability directly in web browsers without costly hardware. So overall, making it more accessible for students in these underprivileged communities. Looking into related work with virtual labs that's currently in the industry, Labster is one, and it offers simulated experiments. However, there are costly paid subscriptions that further limit students in underfunded schools from having accessibility to this resource. Within academic projects, I researched that VR-based simulations boost engagement and understanding, but often require high-end hardware, which limits real-world feasibility. So with this project's focus, using A-Frame will prioritize usability and inclusivity, making immersive labs accessible to all students. My project's overview, I chose a very specific lab simulation just to allow the user to understand entirely what I'm planning to do and what the general idea is. So I chose a basic simulation of a volcanic eruption. With this eruption, I used 3D assets for the volcano, the baking soda beaker, and the vinegar flask. And within the A-frame 3D scene, there are instructions used to guide the user to click the baking soda to add it into the volcano, clicking the vinegar to add it into the volcano, and then after both elements are added, the elements disappear and the eruption occurs. With the first iteration, I initially just set up placeholder objects for the volcano, baking soda, and vinegar. These were just general 3D shapes. I believe there was like a cylinder that I used for the baking soda. I used a prism for the volcano, stuff like that. And then the environment itself was a basic outdoor environment because at the time I wanted to have the simulation kind of exhibit like an actual volcanic eruption. But I ended up changing that later on, and I'll discuss that within the second iteration. But overall, by the first iteration, the core interactions worked. You were able to click on the 3D shapes and they would disappear. And to simulate the volcanic eruption, there was just a basic color change. That basic color change was an area that I hope to improve upon for my next iteration as well. Just having more dynamic visuals to simulate that eruption. From this first iteration, I conducted some user testing, and these were the results. I tested, I interviewed 10 participants, um, both STEM and non-STEM affiliated from ages 18 to 23, and assessed the usability, visual appeal, clarity, and educational value of my 3D scene. As we can see here from the numbers, as far as the clarity of instructions, the visual appeal, and the engagement level, those areas scored pretty highly, but the ease of interaction and educational value were scored lower on those ends. And that was mainly due to the user not necessarily getting feedback about why the science reaction was happening the way that it did. So later on, I added instructions to enhance that clarity and educational value. With the second iteration, I included a lot of enhancements. As far as dynamic visuals, I created a color strobe effect and subtle volcanic shaking to make the eruption more realistic. So as far as the color strobe effect, I had the volcano changing from its initial brown color to a white creamish sort of color to kind of showcase that the eruption's happening and the fizz is overtaking the volcano as if it was lava erupting from the top and going to the bottom. I included an error prevention safeguard that prohibited the user from adding the chemicals in the incorrect order because the correct order would be baking soda added first and then the vinegar. But this safeguard prevented the user from being able to add the vinegar first. And this was done just by like allowing the user to still click on the vinegar, but instead of it disappearing, it doesn't disappear, and there is a text output on the screen that says add the baking soda first. So just kindly letting the user know that this is not what they were supposed to be doing and subtly redirecting them. I also included improved readability by centering all of the instructions that popped up on the screen, no matter the order, and including that scientific explanation post-eruption that let the user know exactly what happened in this dynamic. And just based on other user feedback, there were suggestions about an auditory feedback given. So there is a sound effect I included of fizzing that happens when the eruption happens. So based on the secondary user testing, I see improvements in all of the categories with an overall score of 4.8, whereas before with the primary user testing, there was an overall score of 4.5. So there were significant improvements that the participants saw, and they really appreciated the instructional design as well as the multisensory feedback of the colors and the sound. So now I'm going to demonstrate this. The first thing that I'll demonstrate is adding the baking soda and vinegar in the proper orders so that you can hear the auditory feedback. The baking soda is added and it disappears. And there we see the eruption happening with the fizzing and the color strobe lighting changes. And then we have this explanation of how the reaction occurred and why it occurred. And then to allow the user to start over at any time, you can press the redo button. Now I'll show what happens if the user were to add vinegar first, which is incorrect. The user is kindly redirected to add the baking soda first and allowed to add it then, and the reaction occurs the same. So in conclusion, the accessibility brought by web-based VR AR removes hardware barriers, democratizing STEM education. It is an immersive simulation that enhances engagement and conceptual understanding, which overall creates a positive educational impact for students that have the ability to learn using this resource. And there are potentials for a broader application where schools can use similar AR VR tools across various STEM subjects. For future enhancements, if I were to add on to this project, I would definitely want to have more detailed particle effects coming from the volcano so that instead of it just changing color, there was actual fizz seen coming out of the volcano, as well as having dynamic lighting and interactive tools added on to just being able to touch each of the elements. And that is the end of my project. Thank you.